Good morning, ladies and gentlemen. How are we all doing? It's what is it? It's a Wednesday. Oh, happy hump day, ladies and gentlemen. Hope this finds you all safe and well. So we're back for our second chemistry live class of the Easter holidays. I know it's the second week of Easter holidays for some of you. It's the first week for some of you. I wish they get their act together and just get everyone to have the same holidays at the same time, but there we go. So I am live in two places again. I have got my Zoom room on the go with our TT members. Hello, TT members. Kaya, Megan, Yasmina, David, how are we all doing? I can see a few more people in there. Say hello in the chat. If you're in the chat, please, guys, in the Zoom, make sure that your setting at the bottom of the chat, the blue button, is set to all panelists and attendees. So that way, everyone can see the comments that you're making and the questions I'm answering make sense. Those of you in YouTube obviously can't see that, but you can see that. You can just join the free trial. So there's a link in the description below in the YouTube. And that will take you to the chemistry page where you can join the chemistry free trial or the chem and bio, chem and maths, all three subjects. So you can join that free trial, no commitment. And then you can join all these live classes in the Zoom room. You can ask me questions directly in the Zoom room. Okay, so who's in the YouTube? Hello, Abdallah Maths Tutoring. Hello. Welcome. You just woke up. Well, lucky for you, you had a nice little lie in. Hey, ML. Who have we got here? I'm Rip Pal. How are we doing? Just been doing chem for the last hour. Well, hopefully you're going to do another hour with me now. Okay, so who else have we got in the Zoom room? Forrest, Sophia, Umar, Mantaha. Yeah, fancy seeing you guys here again. Yes, absolutely. We got our regulars in here. Hey, MN in the YouTube. Ansh, hello. So what are we doing today? Well, we are doing some calculations. Now, question to both YouTube and the Zoom. What type of calculations, I know we're doing some titrations today, but what type of calculations bother you the most? So when it comes to chemistry, what do you not want to see in your test papers? Okay, what types of calculation do you not like? And that's just me asking for general information, okay? So back titrations is definitely the kind of overriding one in the Zoom. .x H2O questions, redox titrations, back titrations as well in the YouTube chat. Wow, okay, backwards titrations. Yeah, absolutely. Acid-base calcs. Yeah, acid-base calcs, LML. So like buffer calculations and stuff like that, they're pretty freaky too, aren't they? Enthalpy calculations from Megan as well. So I think we've pretty much covered every single calculation here. Nobody mentioned Arrhenius, actually. Okay, water of crystallization is mentioned again, gravimetric analyses. Yeah, buffer calcs. Anything with the titration, says Sophia. Okay, brilliant. So we're going to cover the majority of, I mean, most of you said some form of titration, right? We're going to look at some different titration questions here today. So I'm going to now, ladies and gentlemen, ignore the YouTube chat. So it's not because I'm being rude, it's because it's the live class for the TT members. And of course, you guys get to have a glimpse into what it's like being a TT member and coming to these live classes, okay? So like I said before, if you want to join in the chat in the Zoom room, if you want to be a TT member, you can do that for free with the free trial. Use the link in the description. Now, speaking of links in descriptions, in the Zoom, in the TT members, section where you join the live class, there is a link to the PDF I'm going to be using today. So for TT members, the PDF is the button below where you join this live class. For those of you in YouTube, the PDF link is in the description for this video, okay? So this video is going to be up, like we're going to leave it on the YouTube channel so you can view it whenever, but you can actually download that PDF now. I'm going to be working through this PDF together. There's only 6 questions on it, but we're not here to just smash through the calcs, okay? We're here to learn how to attack them. We're here to learn some techniques and some skills and tips and tricks to make you feel a bit more confident when it comes to these titration questions, because I'd love you to look at a test paper, flick through and go, yes, there's a titration question there because I know I can smash it. That's the type of confidence we want from people. Okay, so the PDF for TT members is underneath the button where you join the live class, and the PDF for YouTube is in the description. So make sure you can see that. You don't necessarily have to print it out. Just make sure you got pen, paper, and calculator handy because you are going to be doing some calcs today. Now, before we start, I want to ask you a question. Does watching people play snooker on TV, now I don't know why I've just picked snooker, literally that word's just popped in my head, but does watching people play snooker on TV make you a better snooker player? No. Okay, you can probably just sit and watch every championship goes on for an entire year and not be any better at snooker, right? So watching videos of people just going through mole calculations and like, oh, we do this next and we do this next. And, you know, watching people do that doesn't make you any better at it, okay? Oh, and if it's chess, okay, you can learn moves and stuff like that. But same with like watching people do marathons is not going to make you better at doing marathons. Watching people play football does not make you a Premier League star. You know, what qualifies you to play for Manchester United? Well, I've watched every game of the Premier League for the last 10 years. No. So what I'm here to do today is teach you some of the tips and tricks that will make you better at titration calculations. Okay, so I've got a few of them. What I'm not saying here is you have to do this every single time. If you use these methods or even some of these methods in the way that I'm showing you today, by the time you've used them like half a dozen times, then you'll be doing it in your head and it will give you a much clearer picture of the line of attack to these multi-step calculations, okay? So, you know, you make mistakes and that's absolutely fine. But moving on from those mistakes and correcting those mistakes and seeing where you went wrong is really, really important, okay? Ola says practice makes progress, not perfect. Absolutely. It's all about making those small gains, isn't it? And it's about using your or learning from your mistakes and moving on and not making those mistakes again. Indeed, at TT, we have our FFS journal, our frustrating fails and slip journal. We've all been there and made silly errors when it comes to titration questions. I know as a teacher, all my years of marking tests and exams and stuff like that, I know like a lot of mistakes that people make in calculations are just really basic ones from, you know, not using the correct MR for a compound, which is just adding up. You've done all the hard work, but if you get an MR wrong, game over, isn't it? Okay, so simple things like that we want to cut out, all right? So what we need to do today, sorry, in the YouTube, how can I join the live class? TT member. So you go into your chemistry course. The second one down on the left-hand side, the second topic down is live class, and you can join the live class there, and that will take you to the Zoom. Okay. So let's have a look at some tips and tricks. We're going to start with question one, OBS. So I'm going to share my screen here. And hopefully, it does this every time. If in doubt, unplug it, plug it back in again. Yes. And we are in. Okay, so what we should be seeing here, ladies and gentlemen, is question one on the PDF. You can find it in the description to this YouTube video. And of course, it's underneath the button that you clicked in the course to download, okay? So looking at this titration, this is what I would call just a straightforward acid-base titration. Nothing to kind of like write home about here, if you like. Okay, so a student carries out a titration to find the conc of some sulfuric acid, finds that 25 centimeter cubed of 0.088 molar NaOH is neutralized by 17.6 of the dilute sulfuric acid. We've got an equation, calculate the concentration of the sulfuric acid. Now, I know a lot of you are probably way beyond stuff like this. You can probably do this in your sleep, but I'm going to use this simple one, so please bear with me, to give you some of the tips and tricks that you can use for some of the more difficult ones that will be coming up, okay? So my first tip, all right, and I want you to make note of this. We're not necessarily, well, we will do this question, but it's not the reason why I put this question in for you to do. It's so I can use it to show you what I mean with these summer tips and tricks, okay? So we've got a titration, and we need to, I think, first of all, have a general overview of what's going on in this titration, okay? So in any titration, we have got a burette, okay? And we've got a conical flask. Standard, all right? So normally we have our unknown in the conical flask and we have our known in the burette, okay? Saffron would back titrations come up in acids bases topic? Possibly, maybe not in A2. It's more of a year one thing, to be honest, rather than a year two thing. So what we've got is, what we need is a visual image of what's going on, because so many times people get confused. So according to this question, what do you think is in the conical flask here? Looking at the numbers in the in the question. What's in the conical flask here? Maz is saying NaOH. Most people say NaOH. The reason it is NaOH is the fact that we have got 25 centimeter cubed, like a perfectly set value. And that's the normal kind of volume we put in our conical flask, isn't it? So this is NaOH, and it is 0.088, I'm going to put moles per decimeter cubed. And then, of course, underneath, we have got the volume, 25 centimeter cubed. So we have a concentration and we have a volume of NaOH in our conical flask. Obviously, then, what's left is our H2SO4, which is in our burette. Now, this is a mean titer, okay, or the titration value, okay? Because, of course, normally we fill the H2SO4, fill the burette up to 50 centimeter cubed, but, of course, it's neutralized by 17.6 centimeters cubed, and that is a volume, of course. Now, using this method, when you've got the more complicated titration questions where you've got loads and loads of information, it really does help. And like I say, you can draw it out, separate bit of paper, something like that, just to be really clear in your mind. First of all, what's in each of your 2 bits of equipment, okay? So exactly what solutions you've got in each of your equipment. But also, this tells you what information you've got when you draw it out of the question, because a lot of the time, like in some of these other questions further down the line, you know, there's a load of information in there. Look at that one, okay? So it's good to draw out that information, get rid of all the fluff from around it, and focus on that that kind of on the basic information you need in order to attack this concentration, okay? Attack this question. So we know where we're at. The next thing is, what is the student trying to achieve? Well, the question here is really clear, okay? Carries out a titration to find the concentration of the sulfuric acid. So our aim, of course, is the concentration of sulfuric acid. Now, what 2 bits of information do we need? Okay, so we need to find the conc of H2SO4, bit of a wonky H. What do we need? Moles and volume of directly, what do we need to find the concentration of H2SO4? Moles and volume. So concentration equals number of moles divided by volume. That is what we need. So we need the number of moles of H2SO4. Okay, we need the number of moles of H2SO4. So rather than focus on the final answer, just take one step back, just one step back. What do you need in order to find that final answer? Okay. Now you can keep working backwards now. Okay. But I find it really, really helps if you just say, right, that's my aim. I need to find the number of moles of H2SO4. You're one step closer to actually, finding your final answer here. Okay. So if you're really stuck, just go one step back from what the question's asking you to find in terms of like, what do I need in order to find that? Okay. So to find the concentration, you need number of moles and volume. Maybe it's a mass that you need to find. Well, in that case, you need a number of moles and an MR. Okay. If you need the MR, you need the number of moles and the mass. Okay. So there's lots of different combinations, but of course, don't forget your 2 equations for mole calcs are going to come in, are playing a pivotal role here. Number of moles equals mass over molar mass, and number of moles equals concentration times volume, okay? If it helps, do yourself a little triangle in the top corner of the page to help you remember, but you've probably used those enough to just know them off the top of your head now, okay? Rich, do I know this method called unit analysis based on units that helps solve a problem if you forget the equation? Yeah, you can use that. I have heard of that, Ola. It's not something I use, to be honest with you, but it's not bad. It's not bad. So method number 1, okay, or idea number 1 is to just sketch out what you've got. Number 2, look at what the question wants you to find and take one step back from that. So what do you need in order to find that final answer, okay? And the third thing is the steps, okay? You need a path through, okay, which is really, really important. So what I want you guys to do, I'm going to give you just 60 seconds because I think this is all it's going to take. I'm going to get you not to do the question, but to write steps in order to find that final answer. So what are you going to do step by step? So give yourself imagine you were giving instructions to somebody else to do this calculation. I want you guys to do that. And I'm going to give you 1 minute starting from now. I'm going to radio silence just for a minute. I want everybody to do this. Okay. So write down your steps. I'm not saying there's just 3. Just write them on a piece of paper. You don't have to put them in the chat or anything, guys. This is for you and you only. You're all right, Muntaha. Don't worry. Okay, that, ladies and gentlemen, is your time up. So your steps for this one: find the number of moles of NaOH in 25 centimeter cubed. That's using concentration times volume. So we've got both of those things there. Use the equation stoichiometry to find the number of moles of H2SO4 in 17.6 centimeters cubed. Okay, so we found the number of moles of H2SO4. That's what we need, step 2. And then lastly, of course, what we need to do here is find the concentration of H2SO4 using number of moles divided by volume. Okay, so there's only 3 steps to this one. Those of you in the chat, in the Zoom here, find number of moles of NaOH, concentration times volume, ratio to find H2SO4, and then of course, number of moles divided by volume. So nice. So what we've got here is a set of instructions in order to carry out this titration. Now, we've all done it before. We've all just plowed in to a big calculation and just ended up kind of meandering away from the path, okay, and getting a little bit confused as to what we do next and so on and so forth, okay? So we're going to go through these steps now just real quickly to show you how to get to the answer, okay? Now, I'll tell you what, I've written the first 2 steps in red. I'm going to come back to that. So step 1, find the number of moles of NaOH in 25 centimeter cubed. So number of moles of NaOH equals concentration times volume. Concentration is 0.088 times volume, which is 25 over 1,000. And that is 2.2 times 10 to the minus 3 moles. Step 2, stoichiometry, number of moles of H2SO4 in 17.6 centimeter cubed. Now notice how I do that. This is technique in order to present your answers, and I'll tell you why in a second. But always say, I'm finding a number of moles in this volume. Because if you just write down number of moles of H2SO4, then you're just kind of like, no, number of moles of H2SO4 in what volume, you know, so be really specific, okay? So number of moles of H2SO4, it is, looking at this equation, it is a 2-to-1 ratio. Okay, so 2 moles of NaOH react with 1 mole of H2SO4. So therefore, it is 2.2 times 10 to the minus 3 divided by 2. Okay, so that is, of course, 1.1 times 10 to the minus 3 moles. Okay, and that's what we've got there. And then lastly, the concentration of H2SO4 equals number of moles divided by volume, which is 1.1 times 10 to the minus 3 divided by, I've already put my volume there, okay? I've already stated in what volume the number of moles of H2SO4 is. So I can easily just put 17.6 divided by 1,000, obviously standard, because it's obviously got to be in decimeters cubed. So that gives us 6.25 times 10 to the minus 2 moles per decimeter cubed. Always put units on there, guys. Always, 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 okay? So these 3 steps are the steps to finding the answer to this one. Like I said, this is a simple calculation, this one. I'm sure this is fairly remedial to most of you, okay? So 2 things I want to point out here. Number 1, the way in which I'm setting this out. This is what I'm calculating, number of moles of NaOH, and I should have really put in 25 centimeter cubed there. Okay, so I'm being really clear in what I'm calculating here. Then I've got number of moles of H2SO4 in 17.6, and then of course the concentration of H2SO4. So what you're doing is you're making it really easy for the examiner or your teacher, whoever it is that's marking this, to give you the marks. Maybe there was a little FFS somewhere in the middle of this calculation. And if you go wrong, if you don't get the correct final answer, at least it makes it easy for the examiner to see where you deserve credit. Okay, so why make their life difficult at the end of the day? You're there to get more marks. You're there to get marks from your teacher, from the examiner. So make their life easy. Okay, make it easy by showing your calculations really clearly and step by step. No harm in using bullet points like this. Okay, you're not being assessed for this type of thing on your level of written communication. All right, it's just bang, bang, bang. These are my steps, and it's really clear. And of course, if you use a little plan like this, then you can just follow it. All right, so I recommend that plan for larger, more complex calculations. All right, so that's number one. The second really important point is the two in red are always your starting points for a titration. Okay, there's never any excuse to go, I have no idea where to start with this. Okay, because there's always something you've got 2 bits of information for, like this, so you can start somewhere. So my advice, and I want you to write this down, any titration calculation, whether it's a back titration, whether it's a redox titration, or just a standard acid base titration, you always start, number one, find the number of moles in your known substance. Okay, so whatever you know, okay, now in this case it's NaOH, usually it's in the conical flask. Okay, sorry, usually it's in your burette. I do apologize. Usually it's in your burette, your known substance. But anyway, find the number of moles of your known substance, and then 2, stoichiometry. Okay, stoichiometry. So that means go to the equation. Okay, and then once you know, and never forget this, once you know the number of moles of one reagent or one product in your equation, you know the number of moles of everything else in there. Okay, so you can use that ratio to find the number of moles of anything else you want in that entire equation, so long as you know one of them. Okay, that's really, really important. Okay, so top 4 points. I'm going to say those again. Number one, if it helps, draw out the equipment, make it really clear in your mind exactly where your reagents are and how much of them you have, including the information you have about them. Okay. Zainab, is it always known concentration in the burette? No. Okay. This is actually an exception, this one, but 9 times out of 10, your known concentration, so yes, your known concentration 9 times out of 10 will be in your burette. Okay. So your known concentration in the burette, your unknown tends to be in the conical flask. Okay. But in this case, it's kind of flipped, isn't it? So draw out the equipment, including all the information you have about those different reagents you have within the burette and the conical flask. Second bit of information here, look 1 step back from the answer that you need. Okay, what do you need in order to find that final answer? And often it's a lot clearer how to get to that point than it is the final endpoint. Okay, so that's really, really important. So 1 step back from your final answer. And the other one is 3 steps to mole calc heaven, ladies and gentlemen. Number 1, find the number of moles in a known substance you have. Always, always your starting point. Then use stoichiometry to find the number of moles of the unknown substance. And you're basically there. Okay, there's, depending on the type of calculation you've got, depending on the type of titration, step 3 changes. But steps 1 and 2, guaranteed the same every single time. Okay, and you've got 2 of the marks straight away just by doing those 2 points, right? So every single time, find the number of moles of your unknown, of your known, and then use stoichiometry. Okay, so stoichiometry might be 1-to-1, it might be 2-to-1. Yeah, we'll just have to kind of wait and see what we come across with these with the ones that we're going to do next. Okay, how do you know it's flipped in this question? I'm a bit confused. Well, we know it's flipped in this question because if you had your conical flask, why would you put 17.6 centimeter cubed in there? Okay, you're going to put like a a nice kind of round number in your conical flask, like 25 centimeter cubes, okay? And you can say that the sodium hydroxide was neutralized by the sulfuric acid. So in other words, this in the conical flask was neutralized by the H2SO4 coming out of the burette, okay? So that's question one. Like I said, nice and straightforward, hopefully for you guys, okay? So we'll move on and we'll have a go of question two. Now, question two, this one's a little different. And sometimes they can give you things that maybe you've never heard of before. Sometimes they can give you a whole range of values in terms of your titration. So a student was given an aqueous solution of iodic 5 acid. What is that, pray tell? Well, it's HiO3. We know this because they tell us, and was asked to find its concentration by titration with sodium hydroxide. So they've given us the equation for this. We're not expected to know it. He rinsed the burette with water, then filled it with iodic acid. So 25 centimeter cubes sodium hydroxide of concentration 0.125. And then were used in each titration against the iodic acid, and the following results were obtained. So very quickly, what's in our burette, ladies and gentlemen, and what's in our conical flask? What's in our burette here? Iodic in the burette, okay? So this is our HiO3 in the burette, and we need to find the concentration, okay? So we don't know the concentration, but we do know the volume, which is, well, it's a mean titer, isn't it? And we need to work that out. Down here, we have NaOH, and we know that there's 25 centimeter cubed. There's the volume, and we know that the concentration is 0.125, and that's our concentration. So again, we can see really clearly where we've got two bits of information, and that's where we start, okay? So the one difference to this one compared to the last one, I would say, is the fact that you need to find a mean titer, okay? So of those numbers, ladies and gentlemen, 1 to 5, which are going to be eliminated from your mean titer here? Which are going to be eliminated from your mean titer? A lot of people saying 1 and 3, 1 and 3, 1 and 6. 1 and 6, Sam? 1 and 3. Okay. So you can say 1 and 3. I think that 18.6 is the mean titer. I would say just 1 only, because these are all within 0.1 of each other, okay? So you got 0.6, 0.55, and 0.7. I would include all of those because you're plus or minus 0.1, right? So it can be 0.1 above and 0.1 below. So I would say that these are within below 0.1 of this, and this is 0.1 above it. So I'd include all of these, okay, in your mean titer. So I would scrap number 1, and that's finding your mean titer, okay? Yeah, it's, dare I say, it may be different for different exam boards. According to the mark scheme for this one, you know what? No, I think you're right. Yeah, okay. All right, let's do that then. Let's get rid of 1 and 3. I think we should go with a consensus here. So 1 and 3. All right, so let's do this. So use whichever of those tips that I just gave you, okay, whether it's writing out the steps in which you need to do, okay, whether it's just stating, all right, well, in order to find a concentration of iodic acid, I need to find whatever that is, okay? And don't forget, your first 2 steps are always the same. Find the number of moles of your known substance, use a bit of stoichiometry to find the number of moles of your unknown substance, and then work from there. You are most of the way there if you do that, okay? So this is another example. I want you to have a go at it. I'm going to give you, how long do we need? I think we need 3 minutes. 3 marks, 3 minutes, and your time starts now. I'm going to pause my sharing, and I'm going to write out my workings just to show you at the end. So 3 minutes has already started, and you've had 10 seconds of it. So we got some answers coming through in the chat on the Zoom. There definitely seems to be one that is more popular than the others. If you've got times 10 to the minus 4, just have a little think about your calculations. Okay, don't forget you've probably missed out a divide by 1,000 somewhere. Okay, because whenever we use in volume, we need to have it in decimeters cubed, don't we? Okay, yeah, there it is. Pennies dropped. Boom. Okay. Good stuff. So that's the typical type of thing, isn't it? That crops up with an FFS, a frustrating fail or slip. Okay, so, oh, time's up, guys. 3 minutes. 3 minutes done. Okay, 0.167. Well, I did this. Come on, where's my resume share? Boom. Okay, so I did my mean titer first, just because the numbers were there. You could have possibly done it like here at this point. That's absolutely fine. But I used 18.6, 0.55, 0.55, all divided by 3. That's 18.57. I just did that to 2 decimal places. Okay. And then, of course, we start with the number of moles of our known, step 1. Then, of course, stoichiometry is 1-to-1. And we could say that here. Okay. We can just put 1-to-1. Stoichiometry next to it, so the examiner knows how you got that answer. You're not just plucking it out of thin air. And then lastly, concentration of iodic acid is number of moles divided by volume, and that is 3.125 times 10 to the minus 3 divided by 18.57 over 1,000, ladies and gents. Okay, so if in doubt, 3 significant figures, ladies and gentlemen, but we can always check in the question, can't we? So put 3 significant figures there. Okay, 3 significant figures there. Really, really important that you just check. Okay, even if it doesn't tell you, use the appropriate number of significant figures. You can only be as accurate as your least accurate bit of data. Don't forget that. Okay. So 0.168 is the answer you got. If you 0.167, I'm sure it'll be accepted, but don't round too early, ladies and gentlemen. Don't round too early. So in terms of your answers, it can be in standard form or in this form, so 0.168. Or if you did 1.68 times 10 to the minus 1, that is absolutely fine as well. Totally acceptable. Okay. So my advice in terms of rounding is try and keep values in your calculator as you're moving through, and then only round at the end where you can. Okay. It is entirely possible. And 9 times out of 10, you'll find if you just leave that number in your calculator, write it down, and then when you come to do the next calc, you'll be using that number, won't you? So, you know, that just kind of ticks through in terms of the process. So was that one okay? Did everyone get the correct answer in that one? Barring any little kind of FFSs and stuff. Oh, would it be safer to divide the centimeter cube by 1,000 in the first step after finding the mean titer? It doesn't matter. It really doesn't matter. You can if you want to, but I tend to do it, you know, when I'm doing the calculation, I stick divided by 1,000 on there. Whenever I see a V, I just assume I got to divide it by 1,000. Okay, so just be careful with that. Great. Shall we just try the next one? So let's have a look at it. Let's analyze it together first and foremost, because this one, ladies and gentlemen, is a back titration. So let me go through with you what my suggestions are for a back titration. Okay, so a student wanted to verify that ammonium sulfate content in a fertilizer was as given on the packet. So we're checking the amount of ammonium sulfate in a fertilizer. All right, so he boiled 4.24 grams, so we got some information here of the fertilizer with 50 centimeter cubed of 1 molar sodium hydroxide solution until no more ammonia was evolved. All right. The residual solution containing excess sodium hydroxide was made up to 250. Now watch out for this, okay? It means you're making up a stock solution here, all right? So this, ladies and gentlemen, is reaction number 1, okay? This is reaction number 1. And it's this reaction, whoops, it's this reaction that's going on here in reaction number 1. So in a back titration, you will always have 2 equations, 2 reactions going on. Reaction number 1, I'm using my shorthand reaction there, okay, is basically the, well, it's this one, isn't it? Okay, so NH42SO4 plus 2 NaOH goes to like X, Y, and Z. They're those basically, okay? We're not really bothered about these, okay? Not really bothered about those at all. What we're bothered about is this. Now, really importantly, this is in excess, okay? Now, we know how many moles of this we had to start with. This is the very basic principle of a back titration. Reaction number one, with a known number of moles of sodium hydroxide. Once that reaction is done, you're going to have some of that number of moles of hydroxide left over. Okay, so let's say I put 10 moles of sodium hydroxide into this first equation. Okay, and just for argument's sake, there's 4 moles of NH42SO4. How many of the NaOH actually react? Careful, Sam. Careful, look at the stoichiometry. 8. So 8 of the NaOH reacts, leaving 2 left over, okay? In excess, basically, all right? So we don't know this. I've just made those numbers up. We don't know how much of this we've got. We don't know how much of this reacted. But after we have done the titration, we will know this. So if we knew we started with 10 moles of NaOH, and after using the titration, we know that 2 are left over, okay? What does that lead us to find out? If we know how much we started with NaOH, we know how much was left over after the first reaction, that means we now know what? Good. We now know the number of moles of NaOH used in reaction 1. Reaction 1. So if we know that, then we can find by stoichiometry the number of moles of ammonium sulfate in there, okay? So I want you to really dissociate what's going on, all right? Now, I'm going to again use another technique here. Okay, so in back titrations, always 2 reactions, have them separate. And let me show you. So reaction 1, okay, we have got 4.24 grams of fertilizer, okay, reacting with NaOH, 50 centimeter cubed. So we have a volume and we have a concentration of 1 mole per decimeter cubed. That's then the solution made up to 250 centimeters cubed containing our excess NaOH. In other words, what's left over. Okay, and this is a really important step. Then what happens next, guys? Look at the question. What happens next? So we've done that first reaction, reaction number 1. We've got reaction number 2 here going on, and this is always our titration. Good, Shania. A portion, and Ola's saying it as well, a portion is taken out. So 25 centimeter cubed portion, okay, reacts with this, okay, 22.65, which is a volume of 0.09 concentration of HCl, okay, and this is your mean titer. This is known, isn't it? Okay. So I want you guys to do or use one of the techniques here, okay? What I want you guys to do in the next, I'm going to give you just 3 minutes again, okay? I want you to write down your instructions for doing this. I don't want you to do the calculation. Maybe if you feel really confident with it, that's absolutely fine, okay? But we're here to learn some techniques, aren't we? So write down your instructions, how you're going to do this, okay? So give yourself a set of instructions and try and give yourself detailed instructions as to what to do. Find the number of moles of this using concentration times volume. Use stoichiometry too, blah, 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 blah. Okay. Now, don't forget the stoichiometry for this reaction 2, it hasn't given us an equation. You need to write your own equation for this one. Okay. We should all know the equation between HCl and NaOH. Okay. I would hope so. So 3 minutes, write your instructions starting from now. And I'm going to do the same. Okay. Okay, 3, 2, 1. And there we go. Okay, so I've got 8 steps, ladies and gents. Okay, so for this 4-mark question, which seems really harsh, it's 8 steps as far as I'm concerned, you know, taking it down to its bare bones. All right, so let me show you what I've got and we can see how it compares to yours. Okay, excuse my rubbish handwriting. So first one is we need to find the number of moles of HCl in our mean titer, 22.65. Oh, thank you very much, Kaya, Leah, and Fatima, putting that in the chat. Find the number of moles of HCl in our mean titer. Always our starting point. Don't forget, point number 2, use stoichiometry. Always, always, always the same. So that gives us the number of moles of NaOH in 25 centimeter cubed. One part that students, you know, a lot of students forget to do is scaling up here. Find the number of moles of NaOH in 250. Remember, we've taken a portion out, all right, to do our titration with. So we need to find all the sodium hydroxide in the entire stock solution there. Then, okay, once we found that, this is basically the number of moles of NaOH that was left over after reaction 1. That is all your NaOH left over after reaction 1. Okay, so we're done with reaction 2 now. We've done with our titration bit here. That's by the by, you know, we figured out how much NaOH is left over. Next step, I want to find the original number of moles of NaOH in reaction 1. I do that by using this bit here. Okay, this is how much sodium hydroxide was originally put into reaction 1. Then find the number of moles of NaOH used in the reaction. Okay, so we've got how much we put in, we've got how much was left over. We just take one from the other, and then we find the number of moles that was used in reaction 1. Okay, yeah, Kaya. So yeah, that's a really important step, that one. Okay, Kaya said she forgot to do that. So that tells us how many moles of NaOH was used in reaction 1. Then, of course, we're back onto stoichiometry using 2 to 1 to find the number of moles of ammonium sulfate. Now we know the number of moles of ammonium sulfate. We need to do as the question has asked us, and that is to find the percentage by mass of ammonium sulfate in the fertilizer. All right. So we've got a mass of fertilizer there, 4.24 grams. So we find the mass of ammonium sulfate. We know the number of moles. We always know the molar mass. So we find the mass of NH42SO4, and then, of course, the percentage by mass at the end, which is, of course, the mass of ammonium sulfate divided by the mass of fertilizer times 100. Okay. So is there any part of that that doesn't make sense to anybody? I'm going to take that as a no. So I just want you to take note here. There, that's your line. This is all about reaction 2, the titration. Okay. We find the number of moles of whatever our substance is that's left over after reaction number 1. Okay. So divide these things into 2. Okay. Separate them out. And it really helps your clarity of thought here. Okay. So yeah, always start from the second one. Always start from the second one. Always start with your titration. Okay. So we use stoichiometry to find the number of moles of NaOH in 25 centimeter cubed, but of course that's just a tiny portion of all of the NaOH that we have. Okay. So all we're doing here in point 3 is timesing that by 10. If we know how many number of moles in 25, times it by 10, that's the number of moles in 250, assuming that it's, you know, homogeneous and so on and so forth. Okay. So why do we not find the number of moles of fertilizer? Well, we don't know the number of moles of fertilizer, okay, because we don't know what else is in it, do we? Ammonium sulfate only takes part of the fertilizer. There's other things in there, okay? So we can't find the mass, the number of moles of fertilizer because we don't know the MR of it. We don't know, yeah? So what I want you guys to do now, if you haven't done so already, follow these steps, okay? I'm going to give you 5 minutes. Okay, if you've already done it, apologies. Okay, but we are looking at techniques here. Okay, so I'm going to leave this on the screen and you can follow it. Okay, and I will explain these steps again. I will show you in terms of numbers exactly what's going on. Okay, Priya, sorry, in the YouTube chat, I've just clocked my eye on that. Then when I talk about stoichiometry, it's molar ratio. Yeah. Okay, bit confused about step 5. I will show you, right? So basically, step 5 is, where are we? this answer here. So I'm going to call this A. Okay, so it's A, the original number of moles of NaOH in reaction 1, okay, that you put into the reaction 1, minus B, which is this one, which is the number of moles that's left over after reaction 1, okay? Anyway, 5 minutes starts now, folks. I'm going to leave this on here so you can actually follow it, all right? And I'm going to write my answer down and show you after the 5 minutes, okay? It is indeed, Sam. Yes, the stoichiometry between NaOH and HCl is 1-to-1. Okay, they're going to assume you know simple acid-base reaction stoichiometry like that. Okay, so like between your common strong acids and bases. Okay, so you should know, sodium hydroxide or maybe like barium hydroxide or something like that reacting with HCl, HNO3, H2SO4. Okay, so I'm going to shut up. I'm going to do the calc, okay? Monica. Oh, wait, it's clicked. I'm glad. I love that sound of that clicking. And that is time, ladies and gents. And that is time. Okay, Sarah. I just want to clear. Sarah's asked a question. I'm still confused. Why wouldn't you divide the number of moles in 250 centimeter cubed by 5 to find the number of moles in 50 centimeter cubed that are in excess? They're two different things, okay? So reaction 1 is you put this in reaction 1, okay? That is a set number of moles. That is, straight from the jar, the NaOH jar, you've put 50 centimeter cubed of 1 mole of sodium hydroxide in there. The reaction takes place, okay? Some of that NaOH is used up. We then increase the volume with water to 250 centimeter cubed. So there's fewer moles in that 250 centimeter cubed than there is in the original NaOH that you put in there. Okay, so this is post reaction in the 250. The 50 centimeter cubed of 1 molar is the initial that you put in. Okay, does that make sense, Sarah? Okay, so let's run through this. Okay, so step by step. Come on. What is it with Zoom windows? Or isn't a way when you don't want them, but then when you want them, they disappear. Right, okay, there we go. So excuse my scroll here. This looks pretty scary. So first step, number of moles of HCl in our mean titer. Always, always, always your first step. So this is conc times volt. So we get 2.04 times 10 to the minus 2 moles of HCl in our mean titer. That means in 25 centimeter cubed of our NaOH, there's also 2.04 times 10 to the minus 4. Because it's, 10 to the minus 3. I do apologize. Same number. Okay, so exactly the same number because it's a 1-to-1 reaction. Now, if we know that there's that many moles of NaOH in 25 centimeter cubed, we scale up, and then in 250 centimeter cubed, we literally multiplied it by 10 to find the number of moles in 250. Okay, so you could write out the equation. Yep. So in this one, it's literally HCl plus NaOH gives you NaCl and water. Okay, it's this bit that we're interested in, isn't it? The HCl and NaOH. Okay. Oh, FFS, Sam. Forgot to write the 10 to the minus 3. Yeah, be really careful. A little bit of advice, actually. Sometimes it's worth put it in your calculator twice, write it down once. Okay. Sometimes weird things happen. Okay. So now we know this is the number of moles of sodium hydroxide left over after reaction 1. That's why I put a line under it. We found that now. We're going to use that later. Okay. Here we find the number of moles of NaOH in our original 50 centimeter cubed that we put into reaction 1 before the reaction happened. Okay. So this is 5 times 10 to the minus 2. So I'm using 1 concentration times volume here. So this is how much NaOH that went into reaction 1. This is how many moles of NaOH left over after reaction 1. Okay, so we've got 2 really clear numbers on this. Okay. And all I'm doing in step 5, and step 5 seems to be in the Zoom chat, a point of consternation for a lot of people. Okay, so we have got our initial number of moles of NaOH into reaction number 1. We've got this, which is our number of moles of NaOH, which is left over after reaction 1. So it makes sense that the difference, okay, is how much was used in reaction 1. Okay, so 5 went in, 2.04 came out. Okay, so obviously the difference between those is how much was used, and that's this here, 2.96 times 10 to the minus 2 moles of NaOH was used in reaction 1. So now we know this value here. This is, what did I say, 2.96? This is 2.96 times 10 to the minus 2 goes in. So obviously divide that by 2 to find the number of moles of NH4 and that's the number of moles of ammonium sulfate. The mass of ammonium sulfate, okay, is number of moles times molar mass. And then once we've got the mass of that, then it's percentage by mass is 1.96 grams divided by the number of moles of fertilizer there, okay, times 100. Okay, that's a big, big question for 4 marks, isn't it? That is a big, big question for 4 marks. Okay, so yeah, it is harsh. It is harsh. Absolutely, I would have given you more, but then I'm not the examiner, am I? So more questions like this in the exam guide, yes, but they are a rarity, aren't they? Back titrations, they are a rarity. So just, you know what? Don't lose any sleep over this. And one thing I will say with back titrations and a lot of titrations, the first bit of information you get, this bit here, is the last bit of information you need. You see it all the time in titration questions, okay? 46.13%. I mean, that'll be down to rounding. Yeah, that'll be down to rounding as you go through, guys, okay? So just careful with your rounding as you go through. Try and do what we said before about keeping that number in your calculator, okay? So that is a big old question there, really big old question. Now, that's fine. They'll give allowances for that. They'll give allowances for that, I'm sure. Okay. Question number 4. All right, we're 3 down, 3 to go. Okay. Now, I'm going to start throwing you in the deep end on these. Okay. So remember, you've got different techniques you can use. You can draw out the equipment, make sure you know exactly what you've got, where it is, and how much of it you have. Okay. What you've got, where it is, and how much of it you have. Maybe use that method whereby you look, see if you can go one step back from that final answer that you need, and then aim for that. Okay. Or you can write yourself out a little plan and go from there. So if there's any year 12s present, this is a redox titration. Okay. Now, you don't need to do those in year 12, but there's no reason why you can't do this because all the information you need is here. So an experiment was carried out to determine the percentage of iron sample of iron wire. So this is pretty much exactly the same method as we used before. Okay. So this is kind of like a back titration. So see if we can plan this out and do it. So 3.35 grams of wire was reacted with sulfuric acid, and it was converted into Fe2 plus ions. So we know there's Fe2 plus present and was made up to 250 centimeter cubed. So we've got 250 centimeter cubed of Fe2 plus ions. Okay. Now what I want to show you here is that obviously we're trying to find the number of moles of Fe2 plus, which is the same as the number of moles of Fe that's going to be present in this 3.35 grams piece of wire. Okay. All that's happened here is the sulfuric acid was excess sulfuric acid reacts with all of the wire, releasing Fe2 plus ions. Okay. We need to write a balanced equation. Our Fe2 plus ions then are titrated against potassium dichromate solution. Okay. So it's a classic redox titration, iron versus dichromate. You're given the 2 half equations here. When we're writing our equation out for the titration, we of course need to merge these 2 together to give the overall stoichiometric ratio, okay, or the molar ratio between the 2. Really, really important that you know how to do that. Does anybody want me to just quickly go through on how to combine these half equations? Give me a yes. Okay, there's a few people in here saying yes. Okay, we can do that. So 2 steps to full equation. All right. Number 1, balance the electrons. So you can see here that the dichromate is being reduced. Okay. So it's gaining electrons plus 6 electrons. The Fe2 plus here is being oxidized to Fe3 plus. So it's losing electrons. We need to marry these 2 up. So of course, this needs, just for 1 mole of dichromate, you need 6 electrons. So what we need to do is multiply everything here by 6. And then all we need to do is just combine the 2 equations and cancel out any common ones, okay? So, of course, these, your electrons, are always going to cancel out because you've just balanced the equation in order to actually do that, okay? So we end up with Cr2O7 2 minus plus 14 hydrogen ions, and that's us done there because we're not using those, plus 6 Fe2 plus, done. So we used all of those. And of course, all we need now is our 2 Cr3 plus, our 7 H2O, and our 6 Fe3 plus, okay, because our electrons are cancelled there. So balance the electrons, merge them together, literally just merge them together. Okay. Now, of course, in our titration, all we're bothered about is the ratio between our dichromate and our Fe2 plus. Okay. So this is a 7-mark question. I'm going to give you guys 8 minutes to do this. Okay. 8 minutes to do this. So your time starts now. Mez is saying that you wanted to do some chemistry revision to procrastinate and avoid some maths revision. Well, you can do maths revision with Ronnie, okay? So you're doing something useful here, aren't we? I just want to check in with our YouTube community. How are we all doing in YouTube? Are we following this okay? Good stuff. No, the equation that I wrote is not the equation for part 1. Okay, that's just the reaction between Fe and sulfuric acid. Okay, it's just a metal plus an acid. So it's a GCSE question, that one. Metal plus acid. Fe plus H2SO4 gives you what? Yeah, I'm sure it is. In the YouTube, they're asking, saying it's a nice change from revising alone. Absolutely. Revision is not just a solo sport. Okay. I always encourage students to kind of like get involved and chat to each other while they're revising. Some of our students in the TT common room in our forum use each other as like accountability buddies as well. I think it was Megan's idea, who's in the Zoom room right now. Kudos to Megan on that. So it's just like, right, by the end of the week, I'm going to have done paper 1 and paper 2 of this year or whatever. So, it's good. People checking in, making sure you've done it. Okay. Accountability is really important, isn't it? Okay, some people finished already. That's cool. You've got half your time left. You've got another 4 minutes, guys. Another 4 minutes. So don't forget, major learnings from today, all right, when it comes to attacking titration calculations. Number one, draw out your equipment, say what's in it and how much of it you have. Always really helps you to draw that information out of the question, okay? Number two, try aiming for one step back from the final answer. What do you need to find in order to get that final answer? Okay, so here, of course, one step back would be, I need to find the mass of iron, okay, Fe. That's what you need to find. And the other really important one is that the first two steps in any titration calculation, find the number of moles of your known value. That should be really easy to spot if you've drawn your equipment, and whatever you've got 2 bits of information for, that's your starting point. And the second thing is stoichiometry. So the first 2 steps, always the same, every single time, okay? Some people putting the answers in the Zoom chat, which is awesome. Anybody in the YouTube have an answer yet? If you have, just pop it in the chat there. So David, can't remember how to do the first part of this. First part is find the number of moles of what you know. What do you know? Well, you know the concentration and volume of dichromate, don't you? Okay, so find the number of moles of your known substance, in this case, the dichromate, and then use the equation, okay, that we've done, the balanced one, the 1:6 ratio, and use that to find the number of moles of Fe2+. Oh, the first part, okay, well, that's just Fe plus H2SO4. You get FeSO4 and hydrogen. So metal plus acid gives you salt and hydrogen, okay? So I don't mean to be rude in any way, but that's GCSE, okay? So knowing, the general reactions of acids and metals and stuff like that, that's all it's asking for. Yeah, that's it. Don't blow it up in your own mind. Don't think too hard about it. That's literally all they're asking for, okay? And actually, it's got nothing to do with the rest of the question, apart from, it's showing you that Fe2+ ion is essentially the same number of moles as Fe that's in the wire, okay? In terms of your time, you have 30 seconds left, ladies and gentlemen, 30 seconds left. Our dichromate is, yes, in the burette. Our dichromate's in the burette. Oh, thank you, Mohammed, in YouTube. I've just seen that. Much appreciated. TikTok, and you don't stop. It is time, ladies and gentlemen. Okay. I don't know why my alarm's so teeny tiny quiet. Right. Let's go through this. We'll fly through this one because I reckon we've got time for one more, guys. Okay. I'm doing an hour and a half today. We've got time for one more. So what we've got here is our steps. Ooh, I'm trying to move it on there. So first of all, find the number of moles of your known substance, okay? So dichromate in 32 centimeters cubed, that's our mean titer, I suppose. Comp times vol gives you 8 times 10 to the minus 4. Stoichiometry, mole ratio, find the number of moles of Fe2+, that's 6 times 8 times 10 to the minus 4. That gives us 4.8 times 10 to the minus 3. But notice why I did this, okay? This is how much the number of moles of Fe we've got in our 25 centimeter cubed. This is another example where they're taking portions out of a larger solution. So 25 centimeter cubed, we need to find the number of moles of Fe in 250 centimeter cubed, because that's where all of our Fe is. So that's why I'm multiplying it by 10 there, and that gives us 4.8 times 10 to the minus 2. The mass of iron, now I'm assuming here that obviously the number of moles of Fe2+ that we have in that solution equals the number of moles of solid Fe that's in the wire. And that makes sense because that comes from this equation up here. Oops, excuse me, over the page. Fe, FeSO4, because essentially this is Fe2+ and SO4 2-, isn't it? Okay, so that's what we've got there. And then lastly, percentage by mass, and that is our mass of Fe divided by the total mass of the wire, 80%. And that was everyone was getting in the chat there in the Zoom. So that's amazing. Well done, guys. Okay. Well done, well done, well done. So we're going to do one more. We're going to do one more. We are going to fall one question short here. Do you want the harder one or the easier one? It's very similar to the fertilizer one. Harder one? Right. Question 5. I am not going to say a word. Okay. I'm not going to say a word. I'm going to leave you guys have a go at this. Okay. Now, from what I remember, I didn't actually put the number of marks in this, but from what I remember, this is worth, well, that's worth 7 marks, that one. This is worth 6 marks, this one. Okay. So try and use what I taught you here. Okay. Be really clear as what it is going on in this experiment. Okay. So you start, it gets a little confusing. Okay. So write down a plan. That's what I would say. And write down your equipment, show what you've got and where, and then you'll hopefully be able to work it out, and I'll talk you through it. I'm actually going to disappear just for 2 minutes and I'll be back. I'm going to start the timer. I'm going to give you 8 minutes again to do this one, and your time starts now. You need to go out. Sorry, Dexter needs to go out. That's why. Thank you for your patience, guys. because we haven't taught variable oxidation state spec points, so I was wondering if I need to know this or not. I mean, you need to understand that transition metals do have variable oxidation states. Everybody needs to know that. The vanadium specifically, like the colors and stuff like that, I know that Edexcel need to know it, and I think it's OCR. One doesn't need to know it. I think it might be AQA. Sam, if you know the number of moles of H2O, is there a way then to work out the individual moles for oxygen and hydrogen? Yes, absolutely. If you just look at how many atoms of each of those are in that molecule, okay, so if you had 10 moles of H2O, you would have 10 moles of oxygen because there's only one oxygen in each one, but you'd have 20 moles of hydrogen because it's H2, yeah? Just we don't need to know about variable oxidation states in my school. I think this. Well, yeah. I mean, Fatima, I don't know what exam board you're doing, but for Edexcel, OCR, and AQA, you all need to know about the fact that transition metals do have variable oxidation states. The school took stuff out. Oh, okay. So you're not doing that as part of your assessments this year. Well, in that case, I mean, redox titrations are important. Maybe not this one, but like the last one we did, that'll be maybe the sort of thing that you get. Yeah, I understand. I'm just going to focus on. I've got 2 minutes. You've got 2 minutes, so I've got 2 minutes to write down the workings here for you. Okay. Well, if you're not doing, some people in the Zoom saying you're not doing redox titrations as part of your assessments, lucky you, lucky you. So you're not getting tested on a whole thing. Same says Priya in the YouTube. Yeah, that's fine. That's fine. But these techniques not only help you with titrations, but they also help you with other things as well, other calculations by writing down what you know and what is different. So it's in different bits of the equipment. Okay. Hey guys, I'm just writing out my answer here so you guys can see it in its entirety. Okay, so just bear with me. Your time is up, but just bear with me because you've been asking me questions. Okay, so give me 2 minutes. Nearly there. Oh. Right. The really difficult part of this, and I told you it was a hard one, is the stoichiometry. Okay, so only give you one of the two half equations you actually need. Okay, so resume share. So what we've got going on here is this VO3 minus. Okay, this is in our original ammonium vanadate 5. All right, now that goes through a couple of different reactions, dissolved in sulfuric acid, then reacted with excess zinc. Essentially, you've converted VO3 to VO2 plus to V2 plus. Okay, and these are all in a molar ratio of 1 to 1 to 1. So if you find this, you can easily find that. Okay. In our burette, we've got the MnO4 minus. That's our known solution. So my first step here was to find the number of moles of MnO4 in our mean titer. Okay, so which is 7.1 times 10 to the minus 4. Now, here's where it gets tricky. You need to be able to have written this equation for the oxidation of the V2 plus back to VO2 plus. Now, whenever you get this, let me just zoom in on this for a second. Again, we're focusing on this highlighted one here. Okay, so how do we do this? Well, we know we need to get from V2 plus to VO2 plus. The only way in which we can get that oxygen into there, okay, the only way we can get that oxygen into there is by using water. And because there's two oxygens, that's why there's two water going into this. So V2 plus reacts with 2H2O to give VO2 plus. We got 4 H plus is left over, and in this case it's 3 electrons. Okay, 3 electrons. So you just need to look at the change in oxidation state here of the vanadium in order to do that. Okay, here it's plus 2, and over here it is plus 5. Okay, so we've gone up by 3, so that means it's lost 3 electrons. Okay, so that's another kind of story there. But combining that with this second equation that we were given, the MnO4 minus 1. I'd remember that one. That's really handy, actually. But we've got a 3 to 5 ratio here, which is probably the most awkward ratio you're ever going to get. So we need to multiply the top one by 5 and the bottom one by 3 in order to make them both 15 electrons. That's the lowest common value you can get to for both. No, Monica, this will not come up for year 12. This is 100% year 13 topic, okay? But we're just applying our steps here, okay? So this is obviously a little niggly year 13 bit. So overall, we get this equation here, this one, okay? 5V2 plus with 3MnO4. Now, just be careful. The electrons are not the only things that you're cancelling here, okay? The electrons have completely disappeared. But you'll notice any water from the left-hand side is gone, because it cancelled out with some water on the right. Any H plus ions on the right have been cancelled out by the H plus ions on the left. So there are other things that you need to cancel here in order to get this overall equation. But you know what? That doesn't really matter. The most important thing is you get this stoichiometric relationship, this molar ratio relationship, 5V2 plus to 3MnO4 minus. So we know how many moles of MnO4 minus we used in our mean titer. Therefore, the number of moles of V2 plus, and it doesn't say the volume of solution given, okay? It's like all of it, okay? So we can just say the number of moles of V2 plus present is number of moles of MnO4 times 5 over 3, okay? Or divide by 3 times by 5. We're scaling up, aren't we, anyway? Because it's a 3 to 5 ratio. And then, of course, we end up with 1.183 times 10 to the minus 3 moles of V2 plus. So looking at this, now we know the number of moles of this. We know how many moles of VO3 minus were present. In other words, we know how many moles of our ammonium vanadate 5 are present. All right. So the number of moles of, the mass of our ammonium vanadate is that number of moles there. We know how many moles of it we have from our titration, times the molar mass, which is given. That's 0.1383 grams. Now, lastly, part of the question is percentage purity is obviously the mass of ammonium vanadate divided by the mass of the substance, which is 0.15 grams, a really small amount, times 100, and that is 92.2%. How did I figure out the V2 plus to VO2 plus? Well, as I say, if there's oxygen involved, okay, so if it was the opposite way around, okay, if you're going from VO2 plus to V2 plus, then the oxygen disappears, doesn't it? The oxygen's got to go somewhere, and we always make water. Okay, we always make water. So we have to put hydrogen ions in, acidify it, and then the hydrogen and the oxygen get used to make the water. So if we were going this way, so the opposite is true, because what we're doing here is oxidizing V2 plus to VO2 plus. We need to put water in to provide that oxygen for the VO2 plus. Okay, and of course we're going to get hydrogen ions left over as a consequence. Does that make sense, Liam? Boom. Brilliant. Okay, so this is about the toughest a titration question will get. What I will do is, because I'm not going to post a mark scheme, I'm just going to give you the answer to question 6 here. X is 1. Okay, we don't have time, I'm afraid, Shania, to go through question 6, but have a go at it and see if you can get X equals 1. Try and use some of the tips I've given you today. Okay, so final parting shot here is this. Okay, there are ways and tips and tricks of attacking these questions. Okay, really, really important that you use these. The more you use them, the easier these questions will get. So in summary, number 1, all right, draw your equipment, draw your burette and your conical flask. Okay, and maybe the 250 centimeter cubed kind of volumetric flask if you're making that solution up to 250, but state what's in it and how much of it do you have. And just by doing that, it's really obvious about what is your known solution or what is your known reagent, okay? And then that's your starting point, okay? Finding a number of moles of that. The other tip is look one step back from the final answer. Oh, I need to find a percentage by mass. Right, well, I'm going to need to find the mass of that substance in order to find a percentage by mass of it, or I'm going to need to find the number of moles, or I'm going to need to find, I don't know, the concentration of it in order to, so one step back from your final answer, and that will just take you one step closer. And then the third and final tip here is obviously the first 2 steps in any titration calculation, including the one that we just did, is step 1, find the number of moles of your known. Step 2, use the reaction equation to use a bit of molar ratio stoichiometry to find the number of moles of your unknown. Okay, so those are my 3 big tips for moving forward. Mole calcs always start with the first 2 stages. Find the number of moles of something and then use stoichiometry in the equation. Always the first 2 steps, and you're halfway there by the time you've got to that. Okay, you're halfway there. So that ends today's live class, guys. I hope you found that useful. I mean, these are difficult, right? And I just wanted to give you something to kind of hang your hat on. I know where I can start. I know I can get half the marks because I know they always start in the same way. So hopefully you found this useful, and you can, even with the most difficult titration questions, then you can use those first 2 points and use those tips and tricks and techniques. Thank you very much, guys. You're so kind. Like, yeah, I really appreciate that. Thank you very, very much. So in terms of you guys on YouTube, hopefully you found this useful. Okay, this is going to stay here, this recording. And you can just come check on this anytime you like. Share the love. Make sure you share with your friends if you enjoyed it. If you found it useful in any way whatsoever, please give us a little thumbs up. That really helps the old mysterious magical algorithm in YouTube for helping other people find useful videos. And that's what we're all about here. Okay, so thank you very much for coming along, everybody. Tomorrow we'll be looking at some organic mechanisms, so something completely different. Obviously, every exam board needs to know some different mechanisms, but there's a lot of commonality there. I'm going to teach you, even if you come across a mechanism, you think, I don't know where to start, I'm going to teach you about how to learn these mechanisms. I'm going to give you some freebies as well in terms of organic cheat sheets and stuff like that to help you learn the organic chemistry. And most importantly, it's my birthday, so we get to do some organic chemistry on my birthday tomorrow, guys. So wear your party hats, okay? And maybe I'll get a little party bag going for you with a little colouring book and some cake in for you. We'll see what we can do, all right? So thank you very much for coming along today, guys. I really appreciate it. I hope that you found it useful. Thank you to those of you that said you did. And yeah, give us a like on YouTube, high five, and I will see you guys tomorrow.